Today we are going to see the electric field due to a thin sheet of charge having infinite size. So for a thin sheet of charge, if it's a plain sheet, the electric field will be perpendicular to the sheet. So let us see the diagram. I have drawn a thin sheet of charge which is placed perpendicular to the board. So the sheet is placed like this. It is having a large number of charges. Charges are there having charge density sigma. We don't know the number of charges, but we know only the charge density sigma. These charges can produce electric field on either direction, towards the right side as well as towards left side. We need to find the expression for electric intensity on either side. So what we will do, we will consider a Gaussian surface. Here a suitable Gaussian surface is a cylinder having two flat faces like this. This is one flat face. The cylinder is piercing the sheet of charge. This is the center region. This is going out like this. This is the sheet of charge. It is passing through. Means the sheet of charge is perpendicular to the Gaussian cylinder is perpendicular to the sheet of charge. If this is the sheet of charge, this is the Gaussian cylinder. It is penetrating like this. It is going like this. Means the electric field lines will come out through these two flat faces. These field lines will pass through these two flat faces. Since the cylinder is perpendicular to the sheet of charge, no field lines will pass through the curved surface. So we can apply Gauss's law. So we have the area of the flat face at dA. Here also we have area of flat face at dA. This is the direction of electric field at this point. Vector E. Area vector also having same direction, and dA is the area vector. Here also we can draw the electric field, and the area vector dA is also having the same direction. Now we will apply Gauss's law. We need to find the total flux enclosed by the Gaussian cylinder. So we can see that total flux, the flux through this area dA is, by Gauss's law we know it is phi1 is equal to E dot dA, but we know it is E into dA because angle between E and dA is 0. So you will get E into dA. Similarly through this phase E into dA, so we can write phi2 is equal to E into dA. Again through this curved phase there is no flux coming out. So we can say phi3 is equal to 0. So what is the total flux enclosed by the Gaussian surface? There are three regions for the Gaussian cylinder. Two flat faces, one flat face and other flat face, and this is the curved face. Through curved face there is no flux. So what is the total flux? Total flux, we need to add these three fluxes. We will get EdA plus EdA to EdA. This is the total flux. Now we will find the total charge enclosed by the cylinder. We need to consider only the charges within this circular region. Circular region having an area dA. So what is the number of charges within the circular area? Sigma is the charge per area. We need to multiply the area dA to get the total charge. Total charge is equal to sigma into dA. Now we need to apply Gauss's law. Gauss's law says that total flux is equal to 1 by epsilon 0 times the total charge enclosed. So 2E dA is the total flux. It is equal to 1 by epsilon 0 times charge. It is sigma dA. Rearranging, you will get E into dA. Cancelling dA, you will get E is equal to what? Sigma by 2 epsilon 0. This is the electric field due to a thin sheet of charge having infinite size. So we are considering a thin sheet of charge. Charges arranged in the form of a thin sheet. So the charges on the sheet can produce electric field on both sides, towards right side as well as towards left side. Now the electric field does not depend on distance. Means the electric field nearer to the sheet, away from the sheet. So at different points, electric field will have constant value because these are constant values. So when you plot a graph between electric field and a distance, this is electric field and this is the distance, we will get a constant value. So we will get a straight line parallel to the x-axis. Now what we are going to consider is, we are going to consider not a thin sheet, we are going to consider a plain conducting sheet like this. We have a plain conducting sheet likewise, means it has some thickness. So for a conductor, the charges will remain on the surface. So if we give charges, it will remain entirely on the surface. On this side, we can consider charges, as well as on the back side there will be charges. On the back side also there will be charges. We need to consider charges on both sides, this side as well as back side. Again, we are considering the Gaussian cylinder as we have done in the previous case. This is the Gaussian cylinder passing through the plane conductor. We need to consider charges on both sides. So applying Gauss's law as we have done here, we need to consider the flux through this phase, flux through this phase. This is the electric field E. Here also electric uniformly, charges are spread uniformly, so electric field E we need to consider. This is the area vector towards left side. Here the area vector is towards the right side. We need to consider flux through this flat face, and through the curved surface. Curved surface, no flux. So what's the total flux? Total flux equal to EdA plus EdA, as we have done here, 2 EdA. Now what is the charge enclosed? We need to consider charge on both sides. So the charge enclosed will be, charge enclosed to one side will be sigma into dA. Back side also sigma into dA. So 2 sigma dA will be the charge enclosed. So applying the Gauss's law as we have done here, we will get 2 EdA, the total flux 2 EdA is equal to 1 by epsilon 0 times charge enclosed 2 sigma dA. So the dA and 2 cancels. You will get E is equal to sigma by epsilon 0. This is the electric field due to a plane conducting sheet. A plane conducting sheet has charges on both sides. For a thin sheet of charge, the charges on the sheet can provide electric field on both sides. But for a plane conductor, charge on this surface will produce electric field in this direction. Charge on the back surface will produce electric field around this direction. So we need to consider 2 times charge on our left face as well as right face. Here only one charge enclosed in one side. Okay, so we have got 2 similar results. This is sigma by 2 epsilon 0 for an infinite thin sheet of charge. This is for a plane conductor, sigma by epsilon 0. Okay, thank you.